Hello, good morning. We're going to go ahead and get started. Thank you so much for coming today. Welcome, everybody. We're really excited to present our leak loss model research with you today. My name is Kendra Olmos. I'm the Executive Director for the Center of Water Energy Efficiency here at UC Davis. And I'm going to start off with a little bit of context about our webinar today. A while back, we were originally under contract with the State Water Resources Control Board to develop an economic leak loss model. This was to support the water loss performance standards. We did develop a draft of our model, but after that, we parted ways with the state board. We did, however, get to continue developing the model and did finish it, and we turned it into an economically optimal leak loss model. We then analyzed its performance and compared it to a few other models and standards in the leak loss space. We used over 800 utility data sets from 4 different states, and that work we wrote up and is currently in the publication process. We're hoping that the publication is out by the end of the year and we'll be able to distribute it. Since then, we were able to continue the work and create the study all over again, just using California-specific utility data. This is so we could tailor the results to California only, and we use the most updated state water board model to compare it to. And that is what we are going to present today is our observations with the California-specific study. So getting started here, just a few logistics. Actually, we're going to do a poll real fast. Let me start the poll just so we can see where everybody is coming from today. And then I'll go over a few logistics. So we are going to do about a 45 minute presentation, and then we'll go into a panel discussion, Q&A session with the 4 researchers that were involved in the study, led the study. We will do our best to answer everybody's questions, although if we have a large amount, we might not be able to finish. So in that case, we are planning on doing a couple follow-up discussion sessions so we can get more in detail and have a more in-depth discussion and make sure everybody's questions get answered. So keep an eye out for that. We'll be promoting that in the next week or so. This session is being recorded, and then we will email out the presentation as well as put it on our website along with a PDF of the presentation. So I'm going to end our poll here. All right, primarily water suppliers here today. Well, again, welcome everybody. Going to give a quick introduction to our Center for Water Energy Efficiency, or as we like to call SWRCB. Our center focuses on advancing water management solutions through water efficiency and addressing the link between water, energy, and climate. We do this through data-driven science, engineering, and economics in a variety of different fields encompassing the water sector. And next slide. I'm now going to give the bios of our speakers today, and these are the 4 researchers that led this research. We have Katrina Ogesso. She is an associate professor in the Department of Agriculture and Resource Economics at UC Davis. Dr. Ogesso specializes in environmental and energy economics. Much of her research centers on the design and evaluation of water regulations and time-variant pricing in the electricity sector. Frank Loge is a professor in the Department of Civil and Environmental Engineering and faculty director of the Center for Water Energy Efficiency at UC Davis. Some of Dr. Loge's research interests are water and energy efficiency, demand management, water reuse, and data analytics. And we have Amanda Rupiper is a postdoctoral fellow in the Department of Civil and Environmental Engineering at UC Davis. Her research focuses on water use efficiency, on-site reuse, and demand management. And Ellen Bruno is an assistant cooperative extension specialist in quantitative policy analysis at UC Berkeley. Dr. Bruno's research addresses economic questions at the intersection of agriculture and the environment. So welcome to you 4. Before I pass it on to Amanda, who's going to give the presentation, I just want to say you can enter in your questions throughout the presentation, and we'll see you in about 40 minutes. Go ahead, Amanda.
All right, thanks, Kendra, for that introduction. As Kendra mentioned, we did create an economic optimum model that was utility specific, and we're calling it an economic optimum model or the UC Davis model, and I will use those names interchangeably. But what we did with that model is we took that model and we compared it to several models, including the State Water Resources Control Board model, which is what we're going to present on today. But we also compared it to fixed percent reductions and non-utility specific models, and evaluated the impact of different modeling choices, as well as the quality of the data. And that really did result in a couple of publications, and Kendra mentioned them as well. One of the publications has already been circulated, largely based on data quality. I have included the citation here, and we're also including it in the chat. So if you want to access it and read more about it after the presentation, you can. And then the second publication, as Kendra mentioned, is in review, and that's largely focusing on structure. So we have one on structure and one on data, and the structure one is to come. So today, kind of how this is all going to break down is we kind of have three sections we're going to work through. The first is just background, and I'll try to go quickly through it because I know a lot of you are familiar with leak components and leak detection and repair. But I will spend a little bit of time talking about the two different models we're going to focus on today, which is the state model and the UC Davis model. So kind of showing you from a very high level perspective, what do these models look like and how do they generally function? That will be necessary because the next two sections are going to look at the consequences of how these models are built. So the next section we'll go through will be structural consequences. Because the models are built in such a way, we see some of these impacts of that structure. So we'll walk through three of them with you. And then we'll talk about the consequences of the data, using the data as it stands in the water audit to populate these models. We had made some observations, which were in the publication that has been passed around, and we're going to highlight some of them here today. So that's kind of how this is going to go. So we'll start with just the background. This figure on the left, which I'm sure several of you have seen before, it's been in many different publications, just shows the different types of real losses. And that's what we're talking about today, real losses. Real losses are physical losses, physical leaks from the system, and they come in different forms. They come in background, unreported, and reported leakage. And when we sum them all together, that's what we mean when we say our current annual real losses. It's the sum of these three types of real losses. And this is a large parameter in the water audit that the utilities report. So current annual real losses is what you're currently leaking. There is some level of loss that's unavoidable, right? We can't be doing a survey every second to catch a leak the moment it forms. We can't be operating at zero pressure. And so there are leaks that are going to occur. And we call that leakage the unavoidable annual real losses. And the difference between what you're currently leaking and what you can't avoid is the maximum possible leak reduction. So you could reduce down to a theoretical minimum. Whether you should or not is kind of the business of these models. Now, the ratio between what you're currently leaking and that unavoidable piece, we call that the ILI. That's your infrastructure leakage index. And we'll talk about that later, which is why I'm introducing it now. If a utility had an ILI of 2, that would mean that it's leaking twice the theoretical minimum, unavoidable amount. And if it had an ILI of 1, that would mean it's leaking the theoretical minimum. There's nothing more that it could do. And so this figure on the left that you're seeing is a figure that's very similar to a lot of figures that have been out there. So this is not a new idea. But this figure is saying, you start at some level of current real losses, and there's some level that's smaller than that that's unavoidable. And somewhere between what you're currently leaking and what's unavoidable is this economic real loss level. And that is what these models are trying to determine. What is your economic real loss level? And you achieve it by different water management or water loss control methods, such as asset management, pressure management, or the focus today, leak detection and repair. Both the state model and the UC Davis model take the concept of doing a leak detection survey and using that to reduce your leaks. So going out, doing a traditional survey using acoustic software or acoustic equipment and listening for identifying, locating, and then repairing the leaks that you find. And so if we were to look at that from a graphical standpoint, both models take this concept where at some point in time here is on our x-axis, and unreported leakage rate is on the y, just unreported, so just the fraction that you would find with a leak detection survey. At some point in time, utilities are leaking at some rate. as time goes on, that leakage rate is going to increase. New leaks are forming, new holes are popping up, and new leaks make it so that the leakage rate is increasing. That rate of increase over time, we call the rate of rise. It's how your leaks are accruing in a system. If you did a leak detection survey and you found those leaks and repaired them, it would drop your leakage rate down, then new leaks would form, and you would do a survey and it would drop it down. And this would continue such that the leakage rate would drop every time you did a leak detection survey and you repair the leaks that you find. And both models apply this concept. Now the question is, should we be doing this? We know we can reduce our leaks this way, but is it cost effective to do this way? And what we have found in our research with the 800 utilities, comparing it to other ways of managing your water supply, such as water recycling, desalination, traditional sources, or conservation, that this is comparable in cost. So what you're seeing here on the slide are different water management methods and cost here on the bottom, cost per acre foot to expand your supply or extend your supply. And what we typically think of when we think of extending our supply is conservation. That's one of the low-hanging fruit usually. And there's a lot of range of costs, but when we compare it to leak detection and repair, which is the focus today, the costs are comparable. And so it is worth looking at it. And this is the cost when we do it economically. So we consider the economic leakage level. So it is worth doing. Now, how much water we can save, is limited, and how that fits in is going to depend on each individual utility, but that is why we're even considering it today. Now, I did talk about or mention at the beginning that we're going to talk about structure and we're going to talk about data, and I want to explain the difference between the two. When I say structure, what I mean is the equations, the calculations, the assumptions that are really built into a model. How does a model function? And when we're talking about the UC Davis model, cost minimization is a big part of its structure. When we talk about the state model, benefit to cost ratios are a big part of its structure. Data then are the actual numbers that go into the model, your defaults, your inputs, your actual number. For example, in the state model, the cost of a leak detection survey is a default. That's a number that is in the model. The current annual real losses, which is pulled from the water audit, is a utility-specific input that goes into the model. Now, we make the distinction between these two because both are necessary and both are somewhat independent of each other. You could have a wonderful, robust structure, but if the data is unreliable, when you plug it into the structure, the output might also be unreliable, right? You need both pieces. And the reverse is true. You could have excellent data that's very accurate. And if the structure is not sensitive or does not represent reality, then the output also will not represent reality. So you need both, and we're going to talk about them separately today. The data that goes into the model is slightly different for both models. The state model has 5 utility-specific inputs, and I've listed them here. That's the current annual real losses, service connections, length of mains, variable production cost, which is a proxy for the value of water. It's actually the only utility-specific economic input, and average pressure. And then it has a whole slew of defaults, rate of rise, cost of a survey, water cost growth rate. Now, these 5 inputs do come from the water audit, and the UC Davis model would say that all of these should be utility-specific. So that's the difference, right? 5 utility-specific inputs in the state model, and the UC Davis model would say that they all should be utility-specific. Now, the state does say that utilities can adjust the defaults if they have reason to and they have support to justify it, although that they might not have that support. So changing defaults might not be the easiest thing to do. Now, when we go and talk about the consequences of structure, which I'm going to show you results of the models side by side, what I want you to see is the results of structure and not data. And so when we are comparing the models, I will actually be using the same data for the 2 different models. So what's in the state model and what's in the UC Davis model, when we compare them, the data is identical. So when you see the results, what you're seeing is the impact of structure, not data. We don't necessarily think it should be that way, but that is what it is. So I just want to make that clear. Structure then, from a very high level, there's a lot more nuances than what I'm going to explain today, but from a very high level, the 2 models function like this. The state model calculates a leak reduction that ensures that at least a benefit to cost ratio greater than 1 is maintained. And the economic optimum, or the UC Davis model, calculates a leak reduction such that the benefits and costs, the difference between the benefits and costs, are maximized. And we'll pull that out a little bit more to explain. So this state model follows more or less a two-step process, where the first step is calculating your standard. The standard is equal to some current losses, whatever you're currently leaking, minus this backlog of leaks that is calculated. And this backlog of leaks is calculated using a leak component analysis, subtracting out your unavoidable, and really looking at, what is your unreported losses that you would find if you did a leak detection survey. It then sets that standard assuming you're going to survey every 2 years, and that is a fixed survey frequency that is set by the size of your system. The next step then says, setting that standard has some costs and benefits. Is that the ratio of those two greater than 1 or less than 1? And if the benefit to cost ratio is greater than 1, then the utility must meet that standard. And if the benefit to cost ratio is less than 1, then the utility has to do nothing. So it's this all or nothing. You either do it or you don't do it, whether or not that benefit to cost ratio is greater or less than 1. If we refer back to this figure, so we showed this earlier, and we were showing how rates of rise drop when we do a leak detection survey. But what the UC Davis model has taken into account is that survey frequency is a choice, right? You can choose how often you survey, and you can choose it to minimize your costs. Surveying here in some point in time and surveying at another point in time, leaks are accruing in between and then dropping when you fix them. The area under this curve represents the volume of water that is lost because of that survey frequency. You could choose to survey every single year, have a survey here, a survey here, a survey here, and you'd have very small triangles, very small volumes of loss, but you'd have high costs of survey, right? So you're balancing the cost of the water lost and the cost of the survey. Alternatively, you could survey every 10 years, every 20 years, right? Have a survey here and have a survey way out here. But then you're going to have this large triangle of water losses. So few surveys, but lots of water costs. So the UC Davis model takes that into account by calculating the survey frequency that is going to minimize these costs. Costs in this case are the cost of doing the leak detection survey, of repairing the leaks that are found, and the cost of the water loss as a result of that survey frequency. Then using that optimum survey frequency, it then calculates a standard in a similar way to the state model, figuring out how much you would find with a leak detection survey, and then sets it based on that optimum survey frequency. On the right here is a plot, which is from one of our utilities in the data set, and this is a total cost curve. So it's total cost on the Y as a function of survey frequency. And what you can see there is some survey frequency that minimizes costs, and that's how the model chooses what the survey frequency should be. As a result of this, the two models are going to result in very different survey frequencies. So under the state board model, the survey frequency is fixed. It's chosen based on size, with the majority of utilities having to survey every 2 years. There are a few utilities that are larger that are going to survey every 2.5 or 3 years, but the majority are fixed at 2 years. The economic optimum model, because it minimizes total costs and sets the survey frequency based on that, you're going to get a larger distribution. So we have some utilities where it's actually more beneficial to survey more often, every year, every half year maybe, and some where it's more beneficial to survey less often, 4 years, 5 years. So just a larger distribution. So that's the background, right? That's just enough to talk about the consequences. So there's obviously a lot more going on. There's lots of little things happening in the background, but this is the general overarching structure of the two models. Moving into this next section, we want to then highlight what are some of the consequences of this. So we're going to walk through 3. We're going to show you some plots, make some observations that allowed us to make these consequences or to make this conclusion. And the first one that we're going to make is that these two models result in similar aggregate water savings, but different individual costs. The observation we made is that fixed survey frequency versus optimal survey frequency results in different utilities' costs to achieve the standards. And this plot is very similar to one you've already seen. So this gray line you've already seen, this is the total cost curve as a function of survey frequency, where the minimum cost is occurring for this utility. It's going to be different for every utility, but for this utility, the minimum cost occurs when you survey every 3 years. This gray line applies to defaults. So in the state model, the default rate of rise is 4 gallons per connection day per year. It is possible that the rate of rise is actually twice that or a tenth of that. And in those cases, these cost curves will change. The optimum survey frequency will change. But what you should notice is when you have a fixed survey frequency of 2 here, relative to an optimal survey frequency, and you look at the total cost here, the consequence of changing the inputs such that an optimum survey frequency maintains lower costs is that utilities are going to pay less per unit of water to achieve an optimized standard. And you can see that here, right? 6.5, the cost here is lower than the cost of that fixed survey frequency of 2. And it's the same in all circumstances. And that difference might not be large, it depends, but it's always going to be less because of that optimization function. By definition, we're minimizing costs. So what does that look like for a utility? What does that look like for our California data set? What you are seeing here is a distribution of costs. So average cost to maintain a standard in dollars per acre foot. In blue is underneath the UC Davis Economic Optimum model. In purple is under the state board model. The median utility under the UC Davis model is going to be paying about $309 per acre foot to achieve this standard and maintain the standard. And the median utility under the state board model will be paying about $304 per acre foot. And this is a density plot similar to a histogram. So you can think of percentage of our data set on the Y here. So this is just the distribution, but what does that mean for the individual utilities? What that means is from our California data set, 93% of utilities are going to have higher costs under the state board model than under the UC Davis model. And that's going to be true because of that minimization function. In terms of actual standards, though, what are they going to have to do in terms of loss reduction? The models are somewhat similar, although there are differences. What you're seeing is a similar plot to the last one, where we have a distribution, density of utilities on the Y. Now on the X, we have gallons per connection day real losses, how much a utility is leaking. In yellow here, this curve, is the current annual real losses that utilities are reporting in the water audit. So the majority of utilities are reporting losses here in this 20 to 25 gallons per connection day range. That's what they're currently leaking. If you apply the state water board model, in purple here, that would say most utilities need to get their leaks down to this 15 to 20 gallon per connection day range. And the economic optimum model is somewhat similar, although there's less utilities that need to do that. And the state board has some lower standards here, whereas the UC Davis model is going to have some higher standards. So this is just a distribution of the standards that each model is going to require. Now, what does that mean for an individual utility? What that means is that 70% of utilities are going to have more stringent standards under the state water board model than under the UC Davis model. And by more stringent, I mean they need to do larger reductions to get their leakage down. Now, 70% will have to do more under the state board. About 19% will do the same under both models, and about 11% will have to do more under the UC Davis model. In the instances where you have to do more under the UC Davis model, it is due to one of two situations. One, that the survey frequency that is optimum is actually less than 2 years, so survey frequency of maybe 1 year, so you're going to have to bring your leaks down further. Or it could be that the benefit to cost ratio was not greater than 1 for the state board model. And so the state model said, don't do anything, just stay at your current leakage level. When they plugged into the UC Davis model, said, well, maybe it's not greater than 1 at a survey frequency of 2, but it is beneficial to survey at maybe 4 years or 5 years. And so that means you're going to have a lower standard under the UC Davis model than the state board. So there is a different distribution, but the majority of utilities are going to have to do more reduction under the state board model. What does that look like in aggregate, right? This is just the individual utility. In aggregate, from 2017 to 2019, the utilities in California reported that about 6% of their distributed water was lost as real losses. So 6% of their distributed water was reported as a real loss. Of that 6%, about half of it is potentially recoverable, and about half of it is unavoidable. There's nothing we can do. If we apply the UC Davis model, that 6% is reduced to about 3.6%, where about 20% of the losses are still potentially recoverable, but not economically efficient to recover. And if we apply the state model, then that losses gets down to about 3.4% of delivered water, where about 14% of the losses are potentially recoverable, but not beneficial to do so. So the losses are somewhat similar from an aggregate perspective, but we need to keep in mind that 70% of utilities will be doing more under the state model, and they will be paying more to do so. Now, I did say that we're using the same data, right? So you have to keep in mind that if you were to actually plug in utility-specific data for all of the defaults in the UC Davis model, which is what we recommend, these numbers may change. So this is what it is using the same data, knowing that if you use utility-specific data in the UC Davis model, these numbers may be different, but the cost will still be a minimum and be less. The second consequence that we observed is that the state model results are not fully utility specific and may reflect this inflated benefit to cost ratio. And I'm going to show you a few figures that explain what we mean or how we came to that conclusion. What you're looking at is a sensitivity plot. On the x-axis, we have default survey cost. The default in the state model is $595 per mile for a survey cost. This is a log-based plot, so 10 times the default is roughly $6,000, and a tenth of the default is roughly $60 per mile. On the y-axis, we have the loss standard, so what each model says your standard should be in gallons per connection day. The orange is what the state model would say this utility needs to do. The blue is what the UC Davis Economic Optimum model would say the utility needs to do. This is one utility. So this is a median utility. We took median values for survey connection, service connections, length of mains, current annual real losses. So for this utility, they are currently leaking 28.8 gallons per connection day, right up here. If you were to plug in the data using the defaults, the state or the UC Davis model would say this utility needs to get their losses from 28 down to 24. And the state model would say it needs to get down to 19.4. If you shifted that survey frequency or survey cost, if you made that survey cheap, right? Now it's only $60. The state model would not change. And the economic optimum model would say, because that survey is inexpensive, you might as well survey more often and recover your water. And if you're surveying more often, then your leakage is going to come down. And so the standard is going to come down. And intuitively, I think that makes sense. And the reverse is true. If that survey is now $6,000, right, it's very expensive to survey, then maybe you don't want to survey as much. Maybe you're going to let your leaks accrue for a while before you do a survey. And if you're letting your leaks build in between surveys, then the standard is going to increase. What happens under the state board model, though, is as the cost of the survey increases, we get some point where the model is going to say, don't do anything or don't change, just do it all, and then don't do anything. And that happens at around 5 times the default survey cost for this utility. And what's happening there is that the benefit to cost ratio is switching. Here it was greater than 1, so the utility had to do everything, meet the standard. And then it jumps to less than 1, so the utility does nothing, stays at where it currently is. And we get this jumping function. And so as a result, the model is yielding this all or nothing sensitivity. You hit it or you don't hit it, depending on that benefit to cost ratio. We noticed something similar when it came to variable production costs, but there's this additional thing that happens with variable production costs. Keep in mind that variable production cost is one of the 5 utility-specific inputs, and it is the only economic input that is utility-specific. This is the same plot as before, only now on the x-axis we have variable production cost. The median cost in our California data set is about $665 per acre foot. So the 2 models would say, 24 and 19.4. This is the state board, and we have the UC Davis here. As the water becomes more expensive, this water is more valuable, the state model does not change. As the water is less valuable, it also does not change. What we see though with the UC Davis model, because it is that minimization function, if we value water highly, it now becomes more advantageous to survey more often, right? If our water is worth $6,000, we should survey more frequently to save it, and that will bring our leaks down. And the reverse is true, right? If it's not worth much, maybe we'll just let it leak for a while, right? So we see one standard not being changed by changes in inputs, and one that is sensitive to it, and I think a somewhat intuitive way. And so these two models are responding very differently. Now, what you might expect to happen here, we don't see. So in that last slide, we saw a jumping function, right? Where you were at a benefit to cost ratio greater than 1. And then at some point you weren't. And so the model says, don't do anything. You shouldn't do anything. And you would think at some point, as we get down to cheap water, the benefit of doing this is not going to be worth it, right? As it gets cheaper, the benefits are going to be less. And so you would think the benefit to cost ratio at some point would jump to being less than 1 and we would do nothing. But we don't see that here. And we don't see it because of this default minimum variable production cost. In the state model, a minimum variable production cost is applied to utilities that have costs that are less than $1,275 per acre foot. What you see here is a distribution from the water audit of utilities reporting their variable production costs in dollars per acre foot, and the histogram here, so it's number of utilities on the y-axis. 75% of utilities are going to be reporting variable production costs that are less than that minimum. And so the observation we made is that under the state model, about 75% of utilities will have this default applied to them that's greater than the variable production costs that they are reporting in the water audit. The consequence then is that it is not going to be utility specific because this is not using their data, but it also may reflect in an inflated benefit to cost ratio. And I say that because some utilities down here might only value their water at $100 per acre foot, $100, $200 per acre foot. When the benefit to cost ratio is calculated, the benefits use this minimum number. So that benefit is going to be 12 times what the utility actually experiences. And that's going to result in these very high benefit to cost ratios that makes it almost always beneficial to do something. And you might have noticed if you've played with the model that changing the value or the cost of your water does very little to impact the standard. And that's just something we have noticed. The third consequence that we observed because of model structure is that when utility-specific data is not used or poor use of this data can lead to inequality in the resulting regulations. And what I want to say is that being utility-specific is difficult, right? This is not an easy thing to do. There are hundreds of utilities in California, and we want to make a standard that's unique for all of them. And that's not easy. So we have to really recognize that this is a very difficult thing that the state is attempting to do. And just attempting to do it deserves a lot of recognition. I truly believe that. Because it is difficult, it's very tempting to just say that all utilities should just have a flat reduction or a uniform standard. They all need to get their losses down to some fraction of their delivered water. That's what's tempting to do. But the consequence of doing that is huge. And so the state, by not doing that, has avoided some big consequences. So I do think we need to recognize that effort. So what I'm showing you here, and I'm going to explain it because this figure is a little bit hard to understand. So I'm going to orient you in just a second here. What I'm going to show you here are two utility-specific models, the state model, which takes in 5 inputs, and the UC Davis model, which takes in utility-specific inputs, with a non-utility-specific model, a uniform standard saying that all utilities need to get their leaks down to 8% of their deliveries. They can only leak 8% of their total water. That's in yellow here. What's being plotted are linear regressions of these 3 models, plus a 95% confidence interval. On the x-axis, we have loss reduction. So a large number means that the utility has to bring their leaks down by a large amount. So they have to do a lot. A small number means that they only have to bring their leaks down by a small amount. They don't have to do very much. On the y-axis is the cost to maintain your standard. This is cost per acre foot. What you're seeing in the yellow here is we have a slope. So utilities that have to do a lot are going to be paying a lot less than the utilities that have to do a little. On top of that, we see this large 95% confidence intervals, which indicates a high variability in the data, a big spread in the data. Under a non-utility specific standard, this one that we're showing here, some utilities are going to be paying $1,500 per acre foot to achieve a standard, and some utilities are going to be paying $200 per acre foot. So setting non-utility specific standards results in utilities experiencing very different costs to achieve their leak reduction. And the consequence is then that some utilities are going to be disproportionately impacted. And this is where we have to recognize that the state using utility specific numbers has avoided this impact in this situation. In purple here is the linear regression plus the 95% confidence intervals for the state board. And then the blue is the UC Davis. And what you're seeing is both of them are flat, meaning whether you have to do a lot or whether you have to do a little, the cost to the individual utility is relatively equal under both models. Now, the UC Davis one is lower cost. And again, that's that cost minimization piece in effect, where it'll be cheaper to do it, but both are going to be somewhat equal across the board. Now, that being said, having fixed defaults, which I think will happen in the state model, results in fixed costs, and there are consequences of that. This figure is a figure you've seen before. And the last time I showed it, I wanted you to see the impact of having a fixed survey frequency versus an optimal survey frequency and what that did to costs. What I want you to see now is the impact of having a fixed default versus having defaults that are utility specific. In the state model, if you use the default, that is fixed here at 4 gallons per connection day. This is just one default. I chose rate of rise. It could be any default. And you fix the survey frequency. What that means is that the costs are fixed. This is the cost that's going to go into the benefit to cost ratio, right? You're on this curve because you're using the default. You're on this line because you're using a fixed survey frequency. However, what might be the case is you might have a utility that's maybe having a lot of leaks accruing very quickly. Maybe they have old infrastructure, right? And so their rate of rise is actually twice as much. Their cost curve is actually up here, right? Twice almost what the cost curve is down here. And so the cost that should go into the model is this, but because the default is fixed and the survey frequency is fixed, the cost that will go into the benefit to cost ratio is much less. Or the reverse is true. Maybe this is a new utility, they're leaking very slowly, accruing very slowly, and the costs are actually much less. If you fix the default and not representing this change in these cost curves, then the benefit to cost ratio is now suddenly going to be off. And so the consequence is that a fixed default, which is not utility specific, leads to this non-utility specific regulation and potentially inaccurate cost calculations. And so your benefit to cost ratio might suddenly be different than what reality is. And so it might not be beneficial to do something, but it might look beneficial, if that makes sense. So those are the consequences we noticed with structure and choices. Now we want to transition a little bit in talking about data quality. These models require utility-specific data, and that data is largely coming from the water audits. And so what I'm going to show you is a lot from the paper that has been passed around. So you might have already heard some of this, but we're going to point out 3 consequences of using the data as it stands today. The first observation we made is that there's this high dependency on defaults in the water audit. So greater than 90% of utilities are using defaults for categories such as customer metering inaccuracies, unauthorized consumption, and there's a handful of categories here. The water audit is an accounting process. It is a water budget. So if you have a number wrong in one category or slightly off in one category, that error will then ripple out and affect the other categories, okay? Of those utilities that did not use the default, so they did know their data or they entered their own data, they were entering values that were between 0 and 800% what the default value was. So if it said the default value is saying 1% of your delivered water is your customer metering inaccuracy, but in reality, this utility did know that theirs was actually 8% or 8 times that. Now that error is 8 times off here, some other default might be two times off or 5 times off or 4 times off. All of those are going to compound and shift how we're calculating our real losses. So now suddenly how much we're currently leaking might be inaccurate, right? Because we were using the wrong defaults or we're using numbers that weren't representative of our utility. And so the consequence of this is that the regulation might not be utility specific. One, because it's not representing the utility, and a lot of utilities are just using defaults. And it might not be accurate because these errors are being compounded such that we're shifting how we're going to estimate our real losses or other aspects of the water audit. That's one observation. The second observation we made is that there's a lot of variability in the data from year to year, particularly when it comes to current annual real losses. And so sometimes the variability in that data can be similar or even greater than the actual reduction that is requested from these different models. And I'm going to give you an example using one utility from our data set. So this is just one utility. In 2016, they reported current annual real losses of 37.7 gallons per connection day. In 2017, they reported 27.3, and in 2018, they reported 1.49, right? So there's a large spread. Which one is real? This one, that one, maybe they're all real, right? But there's a large variability. If you were to plug them into the state model or the UC Davis model, you would plug in your 3-year average, which for this utility would be 22.2 gallons per connection day. Plugging it into the state model, they would say you don't need to do anything, just stay at where you are. Plugging it into the UC Davis model, it would say your optimum survey frequency is 4.5 years. If you do that, it will bring your leaks down to 15.3. What you should notice, though, is that depending on how the utility is reporting their data, they may or may not be in compliance without having to do anything at all. In 2018, here, they're compliant under both models. Next year, they might be uncompliant. So depending on how they report their data, they're either going to meet the reduction or not without having to actually reduce their water. And so the consequence then is that the regulation becomes meaningless. It might not result in actual water savings if you can achieve a regulation simply by changing how you report your data, changing how you use your defaults, changing how you enter the information, if that makes sense. And this is just one utility, right? But this utility is very similar to a lot of utilities we saw in the data set. This is not an outlier. So what I'm going to show you is a distribution of the utilities right now that kind of elucidates how many utilities are going to be impacted by this. In yellow is a distribution of current annual real loss percent change from year to year in the water audit. On the x-axis, we have the average percent change reported in the water audit and number of utilities on the y, so it's a histogram. The median utility in the water audits are reporting a percent change in their current annual real losses of about 33%. So one year they might be saying they're leaking 100 gallons per connection day. The next might say 133 or 67, right? That's how their data is changing every year. Below it, we have then the percent reduction that each model would say these utilities need to make. In purple is the percent reduction the state board would say they need to make, and in blue is the UC Davis model. The median utility under the UC Davis model needs to reduce their losses by about 34%. The median utility under the state model needs to reduce their losses by about 38%. But we have a large number of utilities that only have to reduce their losses by 5-10%. If the model says you need to reduce your losses by 5-10%, but you're reporting changes in your data of 20-25%, then the reduction is going to get lost in the noise, right? You won't even see the reduction because your data fluctuation from year to year is greater than the reduction. And so again, the consequence is that the regulation can become meaningless. And this is not the point. The regulation is meant to reduce your water physical losses, but the way the data stands, that might not happen. The third, and this is the final observation, and then I will stop talking for a little while. The final observation that we made is that about a quarter of the utilities in the water audits are reporting impossible leak levels, meaning that they are leaking less than their unavoidable levels. What you're seeing here are 3 distributions from 2017, 18, and 19 of ILIs. And you can recall that ILI is a ratio between what's being currently lost to some theoretical minimum, right? So an ILI less than 1 means you're leaking less than the theoretical minimum. This gray bar here represents an ILI of 1. So anything to the left of the gray bar are utilities that have ILIs less than 1 that are theoretically impossible. And in 2017, it was 12% of utilities that said they were less than 1. 26 in 2018 and 29. In 2019, 28% reported that. Now, the consequence of this is that the data is unreliable for setting these standards as they are, because some utilities don't even have real numbers, right? These numbers can't be right, or something else is happening here. So the ILI is a ratio of a current annual real loss to a theoretical minimum. And it's possible that we don't understand what we're currently leaking. And because of the last two slides, I think that's likely the case. If we don't understand what we're currently leaking, we don't have good benchmarking, then how can we go about regulating it? That's the first thought here. The other possibility is that this theoretical minimum number is off. This theoretical minimum was developed several decades ago, largely in the UK. And it's possible that it doesn't actually represent California accurately. The problem with that is not only are you going to get ILIs that are impossible, but that theoretical process is used in both models, and it has to be, right? When you're modeling, you are in theory saying you would find this volume of leaks if you did a leak detection survey. If your theory is wrong, then what the model says you can do is also going to be wrong. So that is problematic. Whether it's because we don't understand our current annual losses, or whether it's because the unavoidable is wrong, having ILIs less than 1 should send a red flag that something is happening that we need to figure out. So that was a lot. We threw a lot at you. So I'm going to do a really quick recap and then end with kind of how do we get out of this problem? And then I'll turn it over to the panel. So because of the structure, there are 3 consequences. And the 3 that we pointed out today is that, the models might result in similar aggregate water savings, but they're going to do so at higher costs because of that minimization function under the state model. That model insensitivity will result in outputs that are not cost effective nor utility specific, and that non-utility specific models like a fixed or uniform percent reduction or non-utility specific data like defaults can lead to unfair regulations. And because of the data as it stands today, which is largely coming from the water audits, these standards are not going to be fully utility specific and potentially not accurate. And that the variability in the data might prevent actual water loss reductions from taking place. And then the final piece of this data is unreliable for setting standards because we don't have good benchmarking yet. We've seen that in the variability and we've seen that in the ILI. So how do we get there? Right? I do think this is a worthwhile thing to do. California is potentially the first in the world to be doing this. So there are a lot of people watching as we set this for hundreds of utilities. So it is worthwhile to get this right and to take the time to do so. And I think we can, but there are 3 pieces that are necessary. And the 3 pieces are improving existing data quality. That's really the first one. And that improving data quality really comes down to validating this leak component analysis, really saying, are these numbers that we say we are leaking, are they true? And are we actually leaking this type of loss? And this is going to require doing real physical data collection, going out into the field, collecting data, testing your meters, maybe doing a leak detection survey in part of your system. Because if you did a leak detection survey and you said, we're going to find this number of leaks, and then you take it back to the model and the model said you were going to find something different, that's worth knowing, right? So taking a little bit of data and using it to validate the model is going to go a long way, not only to making the model more accurate, but also to building trust and confidence in this model. The second piece is we really should be utility specific where possible. Now, I understand that defaults exist for a reason because a lot of utilities might not have certain data, right? Some of this data is not easy to collect. But refining those defaults and maybe even allowing for a range of defaults will go a long way in terms of getting our benefit to cost calculations more representative. So we're actually representing the utility and giving them the best option for them. And that does require utility specific data. And the last piece is changing the structure. And that really comes down to applying these optimization principles. Allowing survey frequency to be a choice that minimizes cost means that you're going to be using your resources as efficiently as possible, but it also means that now your model is going to be sensitive to changes in inputs, and you're not going to get this do nothing, or do everything, do nothing impact, right? So just adding in optimization principles will go a long way to making this model, I think, more intuitive and more sensitive to actual changes. So these are the 3 pieces. We can get there. It will take some time. But it would avoid a lot of the consequences if we can pull these together. That's all that I have. So I'm going to stop right now and I'm going to pass it back to Kendra for a little bit before we move into the panel.
Thanks, Amanda. We'll move into the panel in a second. I just wanted to say thank you to our sponsor, California Nevada Section American Water Works Association, who sponsored our work to do the California specific study and do this webinar. So thanks so much. Let's see, next slide. Thank you. And I just wanted to give a shout out to everybody, let you know that we do have an affiliate sponsorship program. And this is often the only way we can do really timely research. And I invite anybody to participate in this that is interested in being involved in really important research and spearheading research in the water sector in California. So please feel free to contact me about our program. And then next slide, great. Now, if Katrina, Frank, Amanda, and Ellen, if you can turn your cameras and mics on, we're going to go ahead with the question and answer. And we do have a number of questions coming in, so please keep them coming. And let's see, we will go ahead and get started. All right. So thank you guys for, all right, here we go. How could state board's model be adjusted to avoid the consequences presented? Who would like to take that?
I can take that one.
Okay.
Yeah, so we did talk about a lot of consequences, but there really aren't that many things that need to change to avoid some of these consequences. And the big one really is that fixed survey frequency versus optimal survey frequency. Having a fixed survey frequency and that benefit to cost ratio of 1, we saw a lot of that jumping, but shifting it to allowing this optimal survey frequency can build in these economic optimum principles, which would avoid a lot of the consequences. So that would be one, allowing that survey frequency to be selected such that we're minimizing cost. The second piece is really that utility specific piece. And that is, I know that the state has said that you can change these defaults, but it is difficult to do that. Allowing the utility to change their defaults makes the model more representative, and it's also going to make those cost calculations, most representative. And so that will also avoid a lot of the consequences. So adding in that optimum piece and being utility specific, just adding those alone will avoid, the majority of what we talked about today.
Okay, thanks. And if any of you on the panel want to jump in and do secondary comments, just go ahead. I'll go ahead and move to the next one. Do you think the water savings projected in the models is achievable in real life? And what expectations should we have as a supplier community around the models versus real life?
I can do that one as well. So, these models are based on theoretical water loss calculations. And, these calculations were based on real data at some point, real observations. But when these calculations were made, those conditions might be different than the conditions of California now, right? And this is why at the end we advocate for collecting real world results and validating the assumptions of the model. Because it's possible that what the theory says you're going to find is not what you're actually going to find. And so going out and actually doing one survey will be enormous for fixing that calculation and making these models more accurate. And so I do think collecting a little bit of data will let us know whether this is achievable. So conducting, even one leak detection survey, comparing it and improving the models will just make sure that what we are finding is realistic. And if it's not, we can adjust based on, a little bit of data.
Okay, great. Here's one probably for one of the economists. What are the benefits and challenges of an optimization model versus the State Water Board's fixed model and vice versa?
Thanks for that question. So an optimization model that maximizes the net benefits is one that adheres to the economic principle of efficiency. And efficiency in this context refers to the allocation of standards or water loss reductions across all of the suppliers, such that the total benefits from the water loss reduction exceed the total cost by the greatest amount. And a model that maximizes these net benefits, by definition, will yield this aggregate level of water loss at least cost. And so while a benefit cost ratio that is greater than 1 is good in the sense that it guarantees that benefits exceed costs, it guarantees this break-even point, there still may be room for improvement in that model. And ideally, we want the point where benefits exceed costs by the greatest amount. So this really explains why the cost to suppliers is lower in the UC Davis optimization model than the state board model. However, this can involve, it can make the modeling effort a little bit more involved because it makes certain things, for example, survey frequency, a choice as opposed to a fixed number that is applied to all utilities. And so that can make the modeling effort a little bit more challenging. But survey frequency is a choice, and allowing it to be chosen optimally to balance, costs of the water that's leaking versus the cost of doing the survey, and having that baked into the model is what allows us to reach these minimum costs with the UC Davis model.
Go ahead, Katrina.
Yeah, I was just my name's Katrina Gesso. I wanted to kind of chime in or kind of echo two things Ellen said. That's really kind of unique about this optimization model and just in general, the UC Davis approach to this project, right? And so the UC Davis approach to this project was to really kind of bridge or marry kind of economic principles and engineering principles. And by economic principles, what I mean is that when I go in and I teach an economics class, kind of the number one principle we teach is efficiency. That is, we want to make this pie as big as we possibly can. We want to maximize these net benefits, or the difference between these total benefits and the total costs. And that is exactly what we did when we built this model. We're choosing a standard so as to make the pie as big as possible, or make those net benefits of water loss reductions as big as possible. The second principle we often teach in economics is that flexibility is a good thing. So what do I mean by flexibility here? We mean choosing the survey frequency so as to kind of maximize your net benefits. That is kind of introducing some flexibility so each utility kind of can do what it needs to do to, again, like maximize the size of the pie or maximize the net benefits. And so I think those are kind of two real distinctions of this kind of economic model. And just more generally, we're just introducing some kind of basic economic principles into kind of this engineering framework.
Thanks, Katrina and Ellen. Okay, moving on to the next question. Let's see. How do you think the results of the UC Davis model will change with supplier-specific data versus the default data?
Yeah, I'll answer that one. So we don't know. So what we do know is that it makes the most sense to use utility-specific data and not default values. But we do not have a good sense at this point in time of how the results that we presented today that used a consistent data set across both models, how those results would change if we use utility-specific data. But what we can say is the results would better reflect what that utility should need to do. So whatever the change may be, it will be in the benefit of the utility.
Great, thanks, Frank. Next is, given that we are still learning about water loss data, do you think this regulation should be reassessed in the future for performance and adjusted if needed?
I can take that one. Yeah, I think that's exactly what we think should happen. We know enough to know that there's a lot we don't know, right? We looked at our water audit data, and there's enough there to tell us that we're not there yet, right? We are improving we are seeing, you know, a trend in understanding our data, and we're benchmarking, we're getting closer there. And so we're slowly learning more, but we can't truly benchmark or obtain consistent real loss numbers. If we can't do that, then we can't really have an accurate regulation. And so once we do that, we really should be reassessing. And with this validation piece that I kind of mentioned earlier, like if we do a leak detection survey and we don't find what the model says we should find, then we should be reassessing that model, right? We should change the model so that it represents it, because the model is based on saying the costs and benefits, or the cost curve is saying, if you did a survey, this is what you would find and this is what it would cost you. If you do a survey and that's not what you find, then that model is no longer correct, right? So we need to use a little bit of action to come back and change what we do. So I think it's kind of going to be an iterative process, and it probably should be, especially if we don't have great data. So I think it's good that we're setting it. It'll be really great when we choose the data, and it'll be even better when we take that data and fix our models the second time around.
Okay.
Kendra, can I chime in one thing to follow up on Amanda? One thing about the model is it's also nimble enough to account for new data, right? So as the data improves, you know, even if Amanda hit on kind of why some of the structure of the model might need to be revised, but let's imagine that it's kind of a simple issue of kind of new data coming in. The model can receive that and update, right? So as new data comes in, we should be putting that into the model. So it kind of can be this live type of model that can reflect the current status of data.
Thanks, Katrina. Okay, the next one is, what components of the UC Davis model and the State Water Board model are the same?
I can get that one. I kind of mentioned it a little bit. So, you know, the models do take a different approach when it comes to cost and survey frequency and several things, but the fundamental principle of leak detection and repair is the heart of both models, right? They're assuming that if you did a leak detection survey, you would find some leaks, you repair them, and that's going to bring your leakage rate down. So I'd say that's really the commonality between the two models. Now, how you go about doing that and how you should do it and how that impacts your leakages is different, but the same piece, the piece that is the same, is this whole leak detection piece, going out and doing a survey and using that to bring your leaks down. I would say that's probably the only, or at least the primary, like, similarity between the two different models.
Thank you. Can you explain how the UC Davis cost curve is created or calculated?
Yeah, I can talk a little bit about the cost curve. So Amanda spoke about this a little bit and showed one example of the cost curve as a function of survey frequency. So essentially, we wrote out a cost function that includes the cost of actually conducting the survey, as well as the cost of the water that's getting lost when in between surveys. And so we can write this out as a function over an infinite time horizon, essentially saying we can survey at some frequency out into the future, and we have leaks accruing as well. And we minimize this cost function and choose the survey frequency that minimizes this cost function. And that's what's graphed, what Amanda graphed in the slides. And what this incorporates, because surveys happen at some point in the future, we need to bring everything to the present value so that we're actually comparing apples to apples. And so this involves discounting to the present. And so surveys that happen farther out into the future are effectively cheaper because of this sort of time value of money. And so that's all being baked into the model. And capturing this trade-off between the cost of the survey over time and the amount of leaks that accrue over time.
Thanks, Alan. Let me see what our next one is here. What are the impacts of each model on disadvantaged communities?
Yes, I could say with our work, we did not look at that. That was outside the scope of our project. But the one thing I can say definitively is that the economic optimum model does result in the lowest cost for all utilities, including those that are categorized as disadvantaged.
Thanks, Frank. How are the water savings different for the average supplier under the UC Davis model compared to the State Water Board model?
I can take that one. We talked about it a little bit in the presentation. So, it depends, right? Some utilities are going to have more water savings or more water reductions under the UC Davis model, and some are going to have more under the state model. But what we saw, and this was kind of a trend, is that for the majority of utilities under the state model, they were going to have to do more reductions, so achieve lower losses, so greater reductions under the state model. So about 70% we saw we're going to have smaller. Now this difference wasn't huge. This is like a 1 to 10 gallon per connection day difference between the two different models. And the distribution is, we plotted the distribution. About 19% of utilities under both our models will have the same standard, and about 11% under the UC Davis model had to do more, had to do this greater reduction. Now, this was all using the same data. So keep in mind, so take this with a grain of salt, that if utilities actually use their own data, that this all could change, right? If they're using different rate of rise or a different infrastructure condition factor in the UC Davis model, then suddenly they might have to do less or more than what is currently at. So, this is just as it stands today. More utilities are doing more reductions into the state model, but that might not continue as data improves. So you just have to keep that in mind.
Okay, thanks. Next one is, why did the benefits of cost ratios appear to be so high under the State Water Resources Control Board model?
I can take that one. I've actually noticed this as well. We heard, I've actually heard that from several utilities saying that the benefit to cost ratios are like 20, 30 in some instances, which doesn't make a lot of sense. A lot of projects, you don't see those kind of benefit to cost ratios. And I think there was a slide where I talked about the minimum variable production cost being set at this, $1,200. And that's one reason, right? For if you're a utility that values your water at $100 or $200, but when you go to calculate your benefit to cost ratio, if the benefits are 12 times that, that's going to make your benefit to cost ratio seem really high. And that's one reason, but that's not the only reason. The second reason I think that is happening is because of how benefits are calculated. So benefits in the state model are avoided water losses. And what they're assuming is that you're going to be at some leakage level that you're starting at. And they're assuming that you just would stay at that leakage level for the time horizon, right? That you're not going to ever do a leak detection survey. And so there's this volume of water that you would lose if you didn't do a survey. And so it's this large volume of water, which you apply this very high variable production cost to. And so the benefit to cost ratio looks really great. The second, or not the second, but the last reason I think this is happening is because the benefit to cost ratio, which decides whether you do this or don't, is being calculated based on the very first survey. And I'm going to explain what I mean by that. The first survey is when you're at some high level and you're going to find all of your backlog of leaks. So you're going to get a lot of water losses that you're going to avoid, right? So this huge backlog. And then the cost is the cost of the survey. The next time you do a survey, the backlog isn't there anymore. And so the benefits of doing that next survey are much smaller and the cost is the same. So that very first survey, the benefit to cost ratio is huge because the benefits of all this water savings, right? You're going to find a ton of leaks with that first survey. But if you're continuing in the future, so this is kind of the problem here. If you continue in the future at that survey frequency every 2 years, the benefit to cost ratio for the second survey, the third survey, the fourth survey, the fifth survey is not that benefit to cost ratio that you're experiencing in the first. And so it might look good to do it the first time around, but then the next time around, it might not even be greater than 1. Does that make sense? What I'm saying? And so when I was showing you figures, when we were doing this work, we made it very clear it's the cost to maintain a standard, not the cost to achieve a standard, because achieving the standard is actually cheap, right? One survey for a ton of water that you'll find. But to stay at that level, you have to keep surveying at that much, and you're not going to find that much water the next time around. So I think those are the reasons why it's high. There could be other reasons, but those are 3 that we noticed as we were looking at the models.
Great. And since you brought up the survey frequencies, there's a couple questions here around surveying. How can we balance the need for higher quality data with the ability to not update the survey frequency? And is there a standard around data quality that utilities need to meet before they can reduce the frequency of surveys? Is that for you, Amanda? Anybody else?
Yeah, I can take it if no one else wants it. Can you say the first part again one more time? Sorry, I just missed the first. Oh, you're on mute.
Sorry about that. 1 second. Yes, the first part is how can we balance the need for higher quality data with the ability to not update the survey frequency?
Yeah, and I think this kind of talks a little bit about what Katrina talks about, and then there's a few things happening in this question. If you're not updating the survey frequency, then it's things change in a system, right? Your rate of rise can change, your infrastructure condition factor can change, and therefore your survey frequency should change, right? It might be beneficial to survey very often right now. Maybe you changed all your pipes and now you're not leaking very much, and so you shouldn't be surveying as often. And that comes with understanding your data, right? So having good data going into the model. If you don't have good data going to the model, you might not be able to advocate for this change in the survey frequency. But it's hard, to say like what data quality you need. I think the second part was saying like what benchmarking data. Is that the second piece, Kendra?
Sorry again, is there a standard?
Is there a standard?
Yeah, is there a standard for the quality of data before they can reduce the frequency of surveys?
I think there should be some standard of quality of data that you want to use in the model. And I think the benchmarking is really that first piece. So the models, both models are very sensitive to what you say your current losses are. And we saw the variability right now, right? Some utilities were shifting by 50% from year to year. So a reduction of 10% wasn't going to be even showing up, right? So that benchmarking piece, I don't know what that needs to be. Like, does it need to be within 5-10 gallons per connection day? That kind of gets at the reduction. If the reductions are 20 gallons per connection day or 20% and your variability is 2%, maybe that's good. If the variability is 50% and your reduction is 5%, then that's not going to be good. So I think we're going to have to kind of balance that out. But yeah, I know that the water audit has done a lot trying to improve data quality and looking at validity scores, and there's a lot going on in that. And I'm not an expert on data quality and validity, so I'm not going to say that this is exactly what you should do, but we have noticed that not doing it, there are problems. I hope that answered it.
Okay, now I'm going to combine a few questions into one, or just read a few of them that are very related. And Frank, I'm going to give these ones to you. A lot of questions around why did the state decide not to use our optimization model? Do we think that the state will incorporate the model or any aspects of it this late in the game in their model development? Or assume the board has heard all these details, what do they say in response? So if you could respond to those types of comments.
Yeah, so I think it's important to recognize kind of our respective roles in this whole process. And so folks in academics, our role is to perform good science and generate good data and good results to help inform policy. Our role is not to actually develop policy. That falls to different branches of government, like the state board or the state legislature. So I really can't answer these questions because those questions really are directed at the state board, and I don't want to attempt to speculate what they may or may not do. But this webinar fulfills kind of our mission of doing good science and disseminating those results to help inform the development of policy. The papers that will come out from this work have the same intent. So I think those are great questions, but I really do think those need to be directed to the state board to answer.
Great, thanks, Frank. And here someone's wanting some clarification. Did I misunderstand, or did the median utility have a lower leak rate requirement in the UC Davis model, but that in aggregate, the leakage rate for the state was lower? Anyone want to think?
I can try clarifying. I think I understand what you're saying. So under the state board model, 70% of utilities are going to have to reduce their leaks more. So they're gonna have to reach a smaller number. And they, on aggregate, it is gonna result in lower water losses. So it's something like 3.4% of our delivered water under the state board model versus 3.6% under the UC Davis model. So there is a little bit more water savings under the state model, but it's not that different. And it has to do with the distribution, right? So 70% are having to do more, but only by a few gallons per connection day. And some are going to have to do less. So, it just depends on the utility. It's not across the board. You have to do more or less if you're under one model or the other, if that makes sense.
Great, thanks, Amanda. This question says, is it possible to calculate a theoretical minimum for California? Not sure if that was enough information for you or not.
Well, if we had a way to calculate the unavoidable annual real losses that everyone agreed to in the state, then I guess in a sense that would represent the minimum. But the challenge, as we've presented today, is there appears to be some issues with how the UARL is calculated, and that presents itself in the ILI values that we showed, and a fair number were less than 1. So I would say, yes, it's possible if we can actually get a methodology to calculate the UARL that worked and that everyone agreed to. But I don't think we're there yet.
Okay.
Can I make one plug for that?
Mm-hmm.
One way to get us closer to that is collecting real data. Like going out, doing a leak detection survey, seeing what you do find, seeing what you can't find, and then using that to inform these calculations, because we know these calculations are maybe not right, and we have enough data to help us suspect that something's happening here. So to get these calculations correct, you need real data. So going out and collecting data will do a long way to fixing that calculation.
How extensive of, going out and collecting data do you mean, Amanda? Like if we're going to do some field data, could a utility, just survey or collect data for one zone? Or, obviously going out and doing a lot of field surveying is taxing. Is there a way to limit that?
I think that depends a lot on the utility. If your system is broken up in neat little zones that you can calculate an unavoidable annual real loss for a zone and calculate what you would find in that zone from a survey, and then you survey it and it's not accurate or how it's off, you can learn a lot about your system just doing a little section of it. If you're just one big pressure zone and you can't separate it out, maybe it's not as useful. So I think that really depends on the utility, how much data you need in order to actually inform this. But I'm not an expert in that, so I'm saying based on what I know from these models, that someone who does a leak detection survey would know a lot more.
How about this one? Why did UC Davis choose to only focus on real losses? Why not include apparent losses? Anyone want to take that one? Frank or Amanda?
I can, unless Frankie you want to.
Why don't Amanda, why don't you say something too? Because I think we'll say two different things. But we focused on real losses instead of apparent losses, largely just because that was the direction that everything seemed to be moving in at the time we started developing our economic model. We have no strong opinion whether or not we should be using real losses or apparent losses. And I think that's almost more of a policy decision than a science decision. But if that decision were made, then we certainly have the ability to modify our existing economic optimum model to accommodate apparent losses. And maybe Amanda, you could talk just a little bit about, holistically what that would involve.
Yeah, I mean, apparent losses, it would be like the same process. We would have to build another economic element into the model where we would say, this is how much it would cost to improve your apparent loss number. This is the cost of the action. These are the benefits of doing that. You would improve some revenue, and this is how much you should do, right? There's going to be some optimum action, this optimum level. So it would kind of follow the same process of what we did with the leak detection survey, but it would have its own entirely separate model to do that. It's this optimum level of apparent losses that you want to recover.
Yeah, and I just would want to emphasize, I mean, if the state went in that direction of focusing on apparent losses rather than real losses, I mean, one common theme here is if that happens, then we really encourage that to be incorporated into the economic model using this economic optimum concept rather than having prescribed default, values that all utilities have to do. So that would be our one kind of cautionary note if real losses were incorporated into the economic model.
Great, thank you.
Yeah, I have one question. I'm looking at them too, but so I just want to clarify that so there's some questions about will we make all this available? Yes, absolutely. So this presentation and our slides will be available on our website. The model itself is currently under review at a journal. So as soon as that moves through the publication process, that whole model will be made available. We also, so that's a written document that has a bunch of math equations in it. And then in some form, we will make our model available in an electronic form. We're gonna have to figure out how that can be done where it's user-friendly, or somewhat user-friendly, but we're happy to make that available as well. So, anyways, you can send us emails or just keep an eye on our website. And then as we are ready to make those available, we will post it with links to these different documents.
Okay, let's see. The state board model uses the greater of the VPC, or the board's marginal avoided cost. Does the UC Davis model use only the VPC?
Yes. Yeah. So whatever a utility says is their variable production cost, that's how we proxy the value of water. There is a reason why the state uses this marginal cost. I understand, we're trying to represent the cost of gaining new water systems, exploring new supplies, but we really want it to be utility specific as much as possible throughout. And so we use the utility specific number for everything, no matter what they reported it as.
I just want to chime in and follow up on that question, which is, again, there's two distinctions between our model and the model produced by the State Water Resources Control Board, and that is kind of the data used as well as the structure of the model. So one, option would be to kind of populate our model with those data, and we will still arrive at different results because also the structure of the model differs, right? And so I think one thing we kind of keep emphasizing in terms of like, what data should we use? How should we update the data? Again, I think we should update the data in real time to the extent possible to reflect differences in utility costs, differences in utility benefits, differences in the quality of the information we gather over time. And we can kind of, again, we can update the model and populate it, kind of inputting these new data entries. And then we could see how kind of we come at different results compared to the State Water Resources Control Board model based on the structure of the model. And then we can also think about differences based on the data used.
Thanks, Katrina. What would you say are the key inputs in each model? Key meaning the ones that have the most impact on the resulting target. It seems like they are different in each model.
I can take that one. Played with them a lot. So the state board, if this is back from the beginning of the presentation, follows, that two-step process where it first calculates a standard and then it applies this like filter, do it or don't do it, depending on the benefit to cost ratio. And so the standard won't change. The benefit to cost ratio can be 50, can be 5, can be 2, but that doesn't change the standard. So the economic pieces, those inputs and those defaults do very little to change your standard, because that's just a do it or don't do it. So it really drives the standard, and it's kind of true in both models, is this calculation of what you would find with a leak detection survey. And that's largely coming from these theoretical equations on leak component analysis and unavoidable annual real losses. And so that's going to be things like length of mains, service connections, pressure. In the state model, they actually also included infrastructure condition factor, and then rate of rise, because if you're waiting a long time, how your leaks accrue impacts where your level is. So those are really the big ones. In both models, UC Davis model doesn't include infrastructure condition factor, but the other ones apply. Now that's all theory, and we talked about, or I mentioned earlier, that if that theory is wrong, then the standard is wrong. So this piece, because it is so sensitive to how much it thinks you're going to find with a survey, actually doing a survey and then correcting it will go miles for getting these accurate. Because it is so sensitive to that, we do need to get that piece right. So anyways, those are the pieces that it's sensitive to, and that's why, because of that two-step approach.
Thanks. What is the average benefit to cost ratio with the UC Davis model compared to the State Water Board model? And is this difference important? Sorry, the average benefit to cost ratio. And is this difference important?
Well, so they're two fundamentally different principles. And so in the economic optimum model, the goal is to maximize the difference between benefits and costs. And in the state board model, it's entirely different. So they're two different concepts that I think are hard to tie together. I mean, Ellen or Katrina, would you like to add anything to that?
I mean, I think we could essentially take our standards and calculate what a benefit cost ratio would be. But we arrived, as you said, explained, Frank, like we arrived at those standards with a different approach instead of by figuring out what amount of water loss reduction creates this greatest distance between total benefits and total costs. I think after the fact, we could go about and try to estimate what the benefit cost ratio looks like. I'm not sure that we did that at all. So I'm not sure we can say, we know because of the fundamental structure being an optimization model, that if we were to compare, the benefit to cost ratio would be greater than what is coming out of the state board model. But I don't think we've ever done that calculation to actually say how much greater.
Yeah, and the one thing I'd add, just so everyone is clear on this, is in our model, we can't say with confidence that the output of the model is resulting in a benefit to cost ratio greater than 1. So the recommendations our model is making are economical from that standpoint. But as I said, we're not viewing it in that way. So yeah, I think we need to wrap up, Kendra.
Yes, we do. I was just about to cut you guys off. So we're at time. We still have a lot of really great questions here. I'm sorry if we didn't get to ones you guys were really interested in. Try to pick the ones that a lot of people were asking. Thank you everyone for participating, and thanks to our panel, for everyone for coming as well. Look forward to getting our recording of this and hearing about our next discussion session that you'll all be invited to. Thank you. Have a great day.